And you guys are all very familiar with the area formula for a triangle, yes? Area is equal to 1/2 base times height. And you could think of it as length 1/2 length times width, but I'll always refer to it as base and height. And one of the unique things about area of triangles, obviously, I'm not going to give you a problem where I say, hey, your base is 10 and your height is 4. What's the area of the triangle? Because that would just be a waste of time. So it's going to be a little more complicated than that. As far as using the easier numbers, the concept that will usually be demonstrated with kind of the easy numbers is the fact that if I gave you a triangle, say triangle ABC, which of these sides, AB, BC, or CA, is my base? What? It's possible that AC is my base. If AC is my base, then my corresponding height is the perpendicular from that base to the opposite vertex. Okay, so here's one possible combination of base and height. The thing, and again, this is what you guys have probably been exposed to previously. This is your base and your height. But in any given triangle, could I have used AB as my base? Yeah, it is possible to use different sets of bases. If that was the case, my height would be the corresponding perpendicular from the base to the opposite vertex, so H2. And then at the same time, BC could have been my base. If BC was my base, 3, then my corresponding height would be this measure here. Oftentimes when I designate the altitudes or heights, I'll use dashed lines just to indicate that they're perpendicular. I'll try to put the squared off boxes too to show the right angle. Okay, but if you see the dashed line, or if I say that it's an altitude or a height, you should know that it's the perpendicular there. Okay, so as far as the working with easy numbers, it's possible you could see a problem like this, where I gave you the following measures. Okay, so if I asked you to find the height of this triangle, H, and you think you'd be able to solve that? And what would be the area formula for this triangle once again? 1/2 base times height. So if you're thinking of your base in terms of 12, the corresponding height for that is your unknown H. But there's another pair of base and corresponding height, right? So you could have also expressed this formula as 1/2 a base of 8 and its corresponding height of 3. And so using that relationship, you could solve for H. The halves cancel. Divide by 12 to isolate your H. And now you get 3 goes into 12 4 times, 4 goes into 8 twice. And so you could come up with the answer that the height is equal to 2. Now, does that make sense? The area 1/2 4 or 1/2 of 8 is 4. 4 times the height 3 is 12. So what would H have to be so that the 1/2 of the base times the height would equal 12 as well? H would have to be 2. Okay. Now the one other thing as far as the simple numbers that can sometimes cause problems is working with triangles that are obtuse. And the reason for that is if my base is one of the shorter two sides in an obtuse triangle, in order to find the corresponding height, you would need to extend your base and then find the perpendicular distance to that opposite vertex. And so it is possible that your height or altitude may fall outside or in the exterior of a triangle. And the only time to guarantee that your altitude will fall in the interior of a triangle is to measure it from the longest side. So if you know all the side lengths and you had to choose one of them for your height, which we will in a sample problem here in just a minute, I'd always encourage you to choose the longest side as your base. That way you'll never have to work with altitudes that fall outside the triangle. They'll always be in the interior. And now, if it's difficult for you to conceptualize that you might have to draw an altitude outside of a circle, you may want to rely on a concept called shearing. And so if you take the vertex of a triangle and you slide it along a parallel to the base, a couple properties are true here, and the main one is that the area remains constant. And so here's what I mean by shearing, and I'm just going to show you in a sketchpad sketch. And so let's say we take a triangle, and then with respect to the base of this triangle, I construct a line parallel through one of the vertices. I can take any other point and slide it along this parallel, and the areas will be constant. The areas will not change. So what that means is if I take this original triangle, let's say I measure its area, and then I compare that to the area of this other triangle, and I'll change the color here. And so if I take this area and I measure it, it's exactly the same. It doesn't matter where I put this point D, as long as it slides along this parallel. Is the area changing for that green triangle? It's not changing at all. So you can shear a triangle. So let's say you start with a triangle that is an obtuse triangle. Well, rather than trying to work with that obtuse triangle, you could visually slide it in, shear it, so that you're working with a triangle in which all the altitudes will fall in the interior. So if it's helpful for you to think of it in those ways, you can. Again, it should make sense. Oops. If you take a triangle and you slide it along this point somewhere, or along this parallel line, these areas will never change. And again, the reason it should make sense is they have the same base. And is the distance between the base and this opposite vertex ever going to change if the line's parallel? No, because otherwise these lines would converge. So the height's always going to stay the same. So if the base stays the same and the height stays the same, then the area will remain constant. And so anytime you hear the term shearing, that's what it's referring to. And just sliding a point along parallel to the base. And when that happens, the area will always remain constant. The one other concept that you're going to see or hear repeated here in this section is dilation. And we talked about dilations when we dealt with circles. A dilation is just a proportional reduction or enlargement of a figure. In this particular chapter, there'll be triangles. And so when you dilate, a couple things, again, hold true. A dilation involves or creates a similar triangle. So the shape the figure itself will be similar to the original. And because of that, or because they are similar, you have the following ratios of parts will always be constant. Okay, so if you dilate a figure, that means you're creating a similar figure that's either an enlargement or reduction of the original. And so any one-dimensional parts will always have the same ratio. And so if I take a triangle and I dilate it by a factor of 3, what that means is the ratio of any one-dimensional measurement, which is what parts represents, the P here. The ratio of parts is always going to be the dilation itself, 1 to 3. So that means the perimeter of this smaller triangle is 1/3 the perimeter of the larger, or the perimeter of the larger triangle is 3 times the perimeter of the smaller. Okay, these corresponding altitudes right here have a ratio of 1 to 3. And any one-dimensional measurement that you're dealing with between these two triangles will be 1 to 3. And again, because we created a dilation, they are similar to each other. So corresponding angles are equal. In addition to the parts being proportional in a 1-to-1 relationship or a m-to-n relationship, the areas will have a ratio of whatever the ratio of their parts is squared. Again, area is a 2-dimensional measurement, so we're going to take the ratio of their parts and we're going to square them. So if we're looking at the ratio of areas between these two triangles that are dilated by a factor of 3, what does the ratio of their areas have to be? 1 squared to 3 squared, or 9. So the ratio of areas between those two triangles will be 1 to 9. Okay, now, this relationship right here may also be expressed. They might just tell you two similar triangles have parts with a ratio of 2 to 3. What is the ratio of their areas? If that's the case, parts are 2 to 3, therefore the areas will be what? Two squared to 3 squared, so 4 to 9. Okay. So it's a real easy concept. Again, SAT often includes